In this video, we're going to talk about the hydrogenation of alkenes and alkynes. So don't confuse this with hydration, right? Hydration, you're adding water across the double bond. Hydrogenation means you're adding hydrogen across the double bond. So pi bonds certainly can be reduced with hydrogen. And usually this is using a metal catalyst. The easiest way to reduce pi bonds is using hydrogen with a metal catalyst. Now it's important to understand that you do need a metal catalyst. So if I simply took an alkene and I tried to react it with hydrogen, I would get no reaction. Therefore, I have to have a catalyst involved in this reaction. So what kind of catalyst? Well, notice I said it's a metal catalyst, and in general, I'm going to use a metal over carbon. That's what that means, a metal over carbon. So M slash C simply means it's a metal that is adsorbed onto charcoal, carbon, right? And the metal can be a variety of different metals. You can use palladium, you can use platinum, you can use nickel, rhodium, ruthenium. There are variations in the reactivity of the metals. So we can actually use some metals to selectively reduce some alkenes over other alkenes, and we'll kind of explore that in later on. But the key is that you get addition of hydrogen across the double bond. And this is always syn addition. So what's happening is hydrogen gets activated onto the metal surface. The alkene then comes in, and you basically have to, the only way that the alkene can interact with the hydrogen is to undergo syn addition. So you're essentially adding two hydrogens across the double bond at the same time on the same face of the pi system. Okay, so that's important to understand that syn addition is occurring because basically the alkene approaches a metal catalytic surface where hydrogen is bound, and only one face of the pi system can be reduced at one time. So let's take a look first at the reduction of alkenes. Understand that all alkenes can be reduced to alkanes. So when I add hydrogen across the double bond, I am producing an alkane. For example, if I take 2-pentene and react it with hydrogen using palladium over carbon as my metal catalyst in methanol, so usually these reactions are run in some polar solvent, then I get a simple alkane. And in this particular case, I get pentane, right? So this is one of the very few reactions where we know how to take a functional group and make it into an alkane. So alkenes can be reduced, they're being hydrogenated into alkanes. There are examples where sterically hindered alkenes are slower to react, and so because of the difference in reactivity, you can often hydrogenate a less substituted alkene selectively. And certainly this depends on the type of metal catalyst that you use. So for example, here I have a diene, and notice one of the alkenes is only monosubstituted, the other alkene is tetrasubstituted. If I react this with hydrogen using nickel over carbon, so nickel tends to be a little bit less reactive than other metals, and so I can selectively reduce the monosubstituted alkene and leave the tetrasubstituted alkene. So every once in a while you'll see a reaction that looks like that. That's selectivity in the reduction. We can also reduce alkenes selectively in the presence of aromatic hydrocarbons. So this is an important feature to understand as well. Remember, benzene ring is, doesn't behave the same way as alkene. So benzene doesn't undergo addition reactions like alkenes. So any of the reactions that we've seen so far, if benzene is in the structure, none of those pi bonds react like the pi bond of an alkene. And therefore, I can simply take this particular molecule, react it with hydrogen over palladium on carbon. Palladium on carbon is a relatively reactive metal catalyst. We're going to see that, if you use something like rhodium, then you can actually get the benzene ring to reduce, but we'll learn that later on. Suffice to say that almost all metal catalysts, except for a very select few, will reduce an alkene but not reduce the benzene ring. And so we get a product like this. So keep in mind the benzene ring is always more difficult to reduce than an alkene. Now, when we react an alkene with hydrogen over palladium on carbon, the palladium on carbon is what is referred to as a heterogeneous catalyst, right? It doesn't dissolve, it's just suspended in solution. So when I add, if I showed you what the palladium on carbon actually looks like, it looks like charcoal. Right? You can order this up, it comes in a bottle, and it looks like charcoal. You add that charcoal to ethanol, and it doesn't dissolve in ethanol, it simply suspends in ethanol. So we dissolve our alkene in the ethanol, and then we suspend that palladium on carbon. That is called a heterogeneous catalysis because they are not in the same solution with one another. Now, oftentimes that makes it pretty easy because you can simply filter off the palladium on carbon when you're done with the reduction, when you're done adding hydrogen to it. But oftentimes you don't get selectivity, and the rate of the reaction is quite a bit slower. So there are some homogeneous catalysts that can be used, and they work in a manner very similar to that of hydrogen. But oftentimes they're much more selective in what types of double bonds they can reduce. So for example, here I have a whole bunch of double bonds, right? I have the benzene ring, which isn't going to be reduced. I have a tri-substituted alkene, and I have a monosubstituted alkene. If I react this with hydrogen using rhodium monochlorotriphosphine, rhodium monochlorotriphosphine, triphenylphosphine, triphenylphosphine. Try to say that, huh? So rhodium monochlorotriphenylphosphine. This is a mouthful, and usually we simply say it's the Wilkinson's catalyst. So this catalyst was developed by a chemist named Wilkinson, very well-known chemist. And the key to this catalyst is that it's soluble in a lot of organic solvents. So it's soluble in ethanol, it's soluble in methanol. The other key thing is that it doesn't reduce substituted alkenes very well. It will only reduce monosubstituted alkenes. Also, if there are other pi systems like carbonyls, ketones, aldehydes, esters, it doesn't reduce those as well. So there's a lot of selectivity in this type of reaction. In this particular case, what's going to happen? You're simply going to reduce the monosubstituted alkene, and all of the other pi bonds stay the same. All right, now we can think about reduction of alkynes. And just like alkenes, alkynes can also be reduced to alkanes. So if I took an alkyne and I treat it with hydrogen over palladium on carbon, well, I'm going to get reduction to the alkene, certainly, but now my alkene will undergo reduction with hydrogen over palladium on carbon to yield an alkane. And so the reduction of the alkyne never stops at the alkene. It always goes to the alkane when we use hydrogen over some metal catalyst. There are, however, what we call poisoned catalysts that have been developed, and these poison catalysts simply halt the reduction to the alkene. And that's kind of a cool little feature, because if I take, let's say, an alkyne and I treat it with hydrogen using palladium, calcium carbonate, and lead, or sometimes you'll see palladium, calcium carbonate, and quinoline. There are all sorts of little variations, and this basically the calcium carbonate and lead or quinoline poison the metal surface. Such that an alkyne can adsorb onto the surface, but an alkene cannot. These were developed by a chemist by the name of Lindlar, and so we call these types of catalysts Lindlar catalysts. Now, understand that when reduction occurs, it is a syn addition. And so when I reduce an alkyne to an alkene, I get cis alkenes, right? Because this is a syn addition. And therefore, I end up getting, in this particular case, cis 3-hexene. Now, what's unique about that? Well, remember when we talk about the stability of alkenes. Trans alkenes are always more stable than cis alkenes. Here is a reaction that allows us to produce the least stable alkene, cis 3-hexene. In all of our reactions to produce alkenes, we always see that the major product is the trans product. Now we finally are able to make the cis product not only as a major product, but as the only product, which is kind of cool, right? So there you have the reduction of alkenes and alkynes. We see that they can be reduced all the way to alkanes, but we also see that that alkenes can selectively be reduced if we kind of tweak the catalyst that we use, and we also see that alkynes can be reduced to an alkene if we simply use a poisoned catalyst.